the recorder on. Thank God. I have to go back and repeat the first part of the class. All right, so now we're recording, and the first 15 minutes of class will be at the end of this recording. And it is, what is it, Wednesday, May 20th, and this is B period stats. Sorry about that. So excited about this last day. All right, so let's go back to where we were. Let's see, we were this guy, I think. Yeah. And we're going to increase the size a little bit. And we're going to go here. All right, so here we are. All right, so we're down here on the bottom half of section 7.2 problems, the second problem set are into lesson problems. All right, so it says a certain population has a mean of 500 and a standard deviation of 30. So mean of this is a little pigtail, or as Mr. Doctor says, 6. Many samples of size 36. Many samples, doesn't say how many. We're going to have an N of 36, and are randomly, and the means are selected randomly, which we always want random selection of one of those methodologies we talked about back in chapter 3, so that we eliminate bias and it's representative of the population. And it says, what value would you expect to find for the mean of the sample? Well, the mean of the sample should be the exact same as the mean of the population. So that's why it's 500. It says, what value would you expect for the standard deviation of the sample means? And we know that formula. So we took the standard deviation of the population and we divided it by our sample size, which was 36. So we got a standard deviation / standard error of the sample of 5. So it went from 30 all the way down to 5. All right, that's a pretty big drop. And again, standard deviation is a measure of dispersion. So if that number decreases like that, we know the data is collecting, congregating around the mean and getting close tied in there. And that's what's made it go from a kind of a box graph to a standard normal bell-shaped curve, which we talk about in number 9. It says, what shape would you expect the distribution of all these sample means to have? Anytime they ask you that with a sample distribution of sample means, it's always going to be those 2 words, approximately normal. All right, are we good on the front side? All right, let me clear up my scribble. All right, let me go to the back side. All right, another scenario, same questions, different scenario. So it says a September 06 USA Today article entitled, Average Home Has More Televisions Than People. And I get a vouch for that at my own home. Stated that Americans watch 4.58, almost 5 hours of television a day. That's a lot. And probably more than that right now with all this COVID stuff, because there's so little that we can do. It says if the standard deviation for the number of hours of television watch per day is 2.1, and a random sample of 250 Americans is selected, the mean of this sample belongs to a sampling distribution, or that acronym SDS. Okay. It says, what shape do you expect the sampling distribution to take? Approximately normal. That's why we're doing it. So we're getting that thing, even if the population wasn't a normal distribution, the sample distribution of sample means always will be, because we keep increasing that size of N. It says, what's the mean of the sampling distribution? And it came up, let me see if that, oh, that should say, that's misread. That should be, what is the mean of the population, which was 4.58 hours. I just noticed that. I didn't catch that when I was doing the answer key. Okay, so that's actually the population, right? It says, what's the standard? Oh, what's the mean? I'm sorry. I'm thinking standard. I'm talking standard deviation, but it's actually the mean. I'm sorry. 4.58 is right. It's right up here. I'm thinking standard deviation of the population. All right, so disregard that. That is properly worded. All right, so what is the standard deviation of this sampling distribution? So we take the standard deviation of the population and we divide it by the square root over n. So here it went from 2.1 all the way down to 0.133. I mean, it shrunk by what? Huge amount. I don't know how many percent that is, but it shrunk by a huge amount. And once again, the standard deviation / standard error is a measure of dispersion. If that number is getting smaller, it means the data is congregating closer and closer together around the mean. Even as that nice standard normal curve. Sorry for the confusion there, number 11. Momentary brain fart.
Happens, sir.
Yeah, that Alzheimer's is kicking me. All right, here we go. Let's see here. Last part of this. Make this as painless as possible. All right. So as a researcher wants to take a simple random sample of about 5% of the student body at each of 2 schools. Unfortunately, the university has 20,000 students and the college has about 5,000 students. Identify each of the following as either true or false and justify your answer. It says the sampling variability is the same for both schools. So variability is a measure of, how varied your population is or your sample is that you're pulling from the population. Well, it's 2 different schools. It doesn't tell us a whole lot. They're very different in size, so they're probably going after a very different type of students. You know, one could be all male, one could be all female, one could be military, one could not. So, you know that the variability is going to be different, right? So it can't be the same. So that just kind of common rational thinking. Says the sampling variability of the university, also factoring into that, these other questions, 5% of 5,000 is a much smaller number than 5% of 20,000. So we're going to have a much larger sample from the university than we are from the college. So that too is going to influence our math and our numbers, which kind of gives you an indication of how to answer these. It says the sampling variability of the university is higher than that for the college. No, because it's going to be smaller because our N is going to be larger because the university has 20,000 students. Right? These are kind of 13 or 14 are very similar questions. It says the sampling variability for the university is lower than that for the college, which is going to be true. Once again, because our variability is going to go, our variability, which is our standard deviation / standard error, is going to go down because our N for the university is larger than our N for the college. And number 16 says, no conclusion about the sampling variability can be stated without knowing the results of the study. Let's see what we're thinking here. No conclusion about the sampling variability can be stated. No, you can conclude. We just did so right here. And that's just based on math. We're going to have a smaller N for the college. We're going to have a larger N for the university. So we don't have to have any of the data. We can make some conclusions. We did it in those questions 13, 14, 15. Just because we know from our previous discussions on this prop set and this whole chapter, as we increase N, our standard error for our sampling distribution is going to get smaller and smaller and smaller. So that's false. Questions on that one? Everybody's excited and thrilled. All right, one more to go. We're good? All right, I got to stop to get to the next one. And I think it's this guy. This is the one we loaded up from, what, Tuesday? Yeah, Tuesday. All right, let me load up just a bit. All right. All right, let's see here, make my pen work. Okay, all right. So it's considering normally distributed population, mean of 43, standard deviation of 5.2, determine the z-score for the x bar of 46.5, and a sample size of 16. All right, so there's our x, there's our mean. This is where you usually have standard deviation at the bottom, but because of it being a sampling distribution, it's the standard deviation divided by Rn. All right, should have come up with 2.69. Hopefully you did. All right. Similarly, in number 2, what do we do different? We change the n from 16 and up to 35. Well, that doesn't make sense. Do the math right. 6.5. It should be a smaller number. Let me just double check why we did that. I messed up here. Let's see, 5.2. Did you get? I'd ask you what you guys got. 5.2 divided by 4 equals 1.3 over 3.4, 3.5, 3.5 divided by 1.3. 2.69 is right. And then this was 3.5 on the top, same deal. What's the square root of 35? It's about 6, right? So it's 5.2 divided by 5.92 equals 0.87. Bear with me. So it is 3.5 divided by, actually I got 4.02. Is that right? 0.2. So why did it do that? 5.2 divided by 5.92 and 5.2 divided by 4. Yeah, I'm a little perplexed. I would have thought this number here would be smaller since we increased the n. Let me just analyze that. Why did we change something? 46.5, 43, 43, 52, 52. Huh. Same means. Did you guys get those same values?
I think so.
Huh. Let's see. We increased the n. That's getting bigger. That was 7. All right. Well, they're still both smaller than the population, which that coincides. I would have thought that would have dropped down. All right. Well, we won't. I'll think about it. Maybe something will ring a bell here as we keep on going. All right. Clear my mess up. Come on, scroll for me. All right. Let's see what we got here. Let's see if I get the whole thing there. Yeah, we can. All right. It says random sample of size 36 is to be selected from a population that has a. Go away. Let me move this out of the way. Why did it shrink on me? Yeah, let me shrink this down a little bit. There we go. That's better. All right. Random sample of size 36 is to be selected from a population that has a mean of 50 and a standard deviation of 10. N is 36. says this sample of 36 has an X bar which belongs to. So we're going to talk about sample distribution, SDSM. What's the shape of this? It's always this. Anytime they ask you what's the shape, it's always going to be approximately normal. All right. It says determine the mean of the sample. All right. So the mean of the sample should be the exact same as the mean of the population. Always, always, always. If not, you got a problem. It says determine the standard deviation, or actually it's the standard error of the sample. So it is the standard deviation of the population divided by our square root over n, which comes out to 1.667. All right. And it says, what is the probability that the mean, the sample mean, will be between 45 and 55? All right, so we had to actually calculate two z-scores, right? Because it's in between. If we drew a little curve of what we're being asked, all right, let's see. We've got 50, right? And it's asking us what's the probability. It's 5 on either side, from 45 to 55. So we're gonna have to calculate the two z-scores for that 45 and 55, so we can figure out what this area is in here. Right? So here's your 45 calculation z-score. Here's your 55 calculation z-score. There's your z-score. Here's the corresponding area. Here's your z-score for 55. Here's your corresponding area. All right. So that first z-score gives us this area. The second z-score at 2.99 gives us everything back this way. And so that's why we subtracted the 0.9987 from the 0.0014. And at 0.9973 is my shaded area here under the curve. Does that make sense? Everybody got that right? Yeah. All right. I know you got it right. I just I feel it. All right.
So we can see.
All right. Second question. Is what's the probability of the mean will have a value greater than 48? So again, I kind of always like to draw a picture because that kind of gives me some direction of how to solve it. So it's greater than 48. So it's asking you for all this way, right? So we got to calculate the z-score for 48, which we do right here, right? And we come up with a negative 1.19. That makes sense because we're on the left side of that mean, so we know it's going to be a negative number. We get this value here, but that's giving us this area right here. So we got to subtract it from 1. So the answer is 88%, 88.5%. That's this, all this shaded area. And I know everybody got that one right. All right. Questions, comments, concerns? Let me erase this stuff. There we go. Side 2, we're almost done. All right, it says, all right, it says consider, let's see, let me shrink this down. The whole thing on there. Hopefully you can see that. Let's see, yeah. Can you read that? I know it's a little bit small. Let's get everything on. Just trying to, yeah. Let's see. Yeah, we'll scroll up if we need to. All right. So here we go. Come on, go away. I got on my way there. Hold on. Over there and then it went away. Well, it comes back every time I use the pen. That's nice. All right, so it says consider the approximately normal population of heights of male college students. Has a mean of 70 inches. What is that? Divided by 12, that's a 70 inches. See, 12 and 70. Let's see, 5 feet is 60. So that's what, 5 feet 10 inches. And a standard deviation of 4 inches. N is 16. All right. Describe the distribution of X of the height of the male college students. If we're going to do a sampling distribution, it's always approximately normal, with a mean of 70 and a standard deviation of the population of 4 inches. For the population, I underline that because we're doing the population first and we'll talk about the sample. Determine the proportion of male college students' height is greater than 71. Z-score calculation. up with a z-score of 0.25. It's 0.5987. And this would be, if we look at it graphically, it'd be 70. And what it's asking you to calculate is 71. So it'd be all this area under here, right? So this 5987 is this area. So of course we've got to subtract from 1. So about 40.1% is over greater than 71 inches. Describe the distribution of X bar and the mean of sample size 16. Magic words once again. Says determine the mean of the sampling distribution. It should be the exact same as the population. Bingo. Do the standard error of the sampling distribution, which is the standard deviation of the population, which was 4 divided by our square root of our sample size, which comes out to a nice even 1, which makes the math nice and easy. All right. Annotate, clear. All right, so last 2 questions. 13, for the sampling distribution, determine the proportion of male students whose height is greater than 71. That's what we did above, isn't it? But we did it for the population. Yep, it's the exact same as what we did above, all right? But it is different because why? Because our standard deviation standard error is 1 versus way up here was 4. So we get a different value of 1. It's 0.8413. It's that same drawing I had before with 70. And we're doing everything to the right of 71, which is all this stuff over here. So we get a smaller number. Why do we get a smaller number than we had above? Because all our data is congregating towards the mean. All right, and it's not going to be out here on either end, or it's not, less of it's going to be out on either end. That's, that's kind of the logical rationale behind it. All right, let's see here. For the sampling distribution, determine the portion of college students whose height is less than 67 inches. All right, and so we just did the same calculation. You got a -3, and it's 0.0013. We don't have to subtract it from 1 because it's asking you to the left of the curve, less than 67, which is the way the table is set up. And you can see it's a small number because, once again, we're doing a sampling distribution of sample means, and everything's congregating towards the mean. And I believe that is it. All right. That's it. Statistics is over. And we got 10 minutes to spare. Any questions on those 3 problem sets? Hopefully you got a lot of the same answers, because again, this, if we had been in school here, we would have gotten into chapter 8 and said, it's kind of like I like the last couple of chapters of statistics because we kind of pull together all the stuff that we've learned the previous 6, 7, 8 months and actually put it to the use in applicable situations. With the COVID thing, it kind of slowed down our progress, but that's the way it is. I appreciate you guys hanging tough in class, particularly this month. I know it'd be easier to take the easy way out and not show up and not do much. So I appreciate you guys are the last 2 still standing tall and not haven't thrown out the white flag or given up.
Yes, sir.
It's been a pleasure having you in class this year.
It's a fun class.
Hopefully we'll see you come August. Be a different atmosphere around here.
Hopefully.
Happens there. I won't get on my political soapbox. But everybody has a safe summer. Maybe see you, plan to be here on the 11th, I think it is, of July, when they're going to do graduation in one way, shape, or form. So maybe see you at that. Mr. Gore, make sure you get out and play some golf.
For sure.
All right.
Yes, sir.
And that JV golf team, undefeated season.
Yeah.
First one ever.
There we go.
Anyway, any questions, comments for me?
No, sir.
Sir.
All right. Well, I hope you guys have a nice summer. I hope this COVID crap restrictions and house arrest becomes less and less. And we kind of get back to a normal way of life with the liberties and freedoms that the constitutions and Bill of Rights afforded us, even though our dumbass governor does.
Doesn't take our guns away.
Yeah, that's net. Well, he he discreetly and quietly passed, him and his liberal Democrat liberal House and Senate did pass several new gun laws kind of quietly and discreetly during all this COVID stuff so that people were paying attention to it. So turd burglar.
Yeah.
So
Isn't it like you can't? Isn't it like you can't? You can only buy like one firearm a month now.
yeah, he restricted the number of firearms, and I think they're still trying to do, classify more firearms as assault weapons, and then kind of ban those from private sales. But, yeah.
I wish I got a stimulus check so I could have bought like an AR-15,
There you go.
but didn't get one.
There you
You
go.
have to be 18 or something like that. I don't know.
All right, but have a good summer, and hopefully see you come latter part. Actually, I don't think I think the calendar, we're not starting school till after Labor Day,
Yeah, I don't. It's
so that they have more time to renovate and make room for our new students,
yeah.
different persuasion.
It's a shame.
All right, I better not say too much more than that, otherwise I may not be back here in the fall. Okay,
All right. Have a good summer.
All right,
so
sir.
y'all have a good summer, and we will see you maybe on the 11th of July.
Sir.
Sir.
Here, bye-bye. Okay, folks, I'm going to go back to the beginning of class because unfortunately I failed to turn the recorder on for the first 15 minutes. So to make sure I've got that covered, we will go back to the beginning of class. And today we are going to cover the 3 exercises and problem sets that we started last Tuesday, last Thursday, and this previous Tuesday that kind of tied up and finished sections 7.2 and 7.3 and completed chapter 7 completely. Okay. All right. So the first exercise from 7.2 was creating a sample distribution of sample means for a population utilizing the numbers 4, 6, and 8. Okay. In class, on PowerPoint, we use the numbers 2, 4, 6. So we're going to apply the same mechanics and methodologies, just our population numbers are slightly varied. So if I got 3 numbers, each one equally likely to occur, there's a 1/3 probability of X of 4, X of 6, X of 8. So we now are going to put this into a frequency distribution table, which we've been utilizing off and on since back in September. All right, to start analyzing the data and doing our inferential statistics. So there's our 3 X's. Each one's equally likely to occur. The sum of all the possibilities is always equal to 1, so that checks. In column 3, it's just column 1 times column 2, which we did here. We sum them up and we come up with 6, and always the sum of X times probability of X is always the mean, which is 6. And in the 4th column is the first column squared times the second column. So 4 squared times 1/3 is 16/3. 6 squared is 36 times 1/3 is 36/3, and so on. We sum those up. And this is the value we're going to need to calculate the standard deviation of this set of data. If we graph the data, we get a rectangle. All right, it's not standard, it's not a normal curve, it's not a bell-shaped curve. All right, now we're going to go down here and calculate our our mean, which we already knew was 6 because that's always the sum of column 3. And then we're going to calculate the standard deviation, which is that sum of column 4 minus the sum of column 2 squared. 6 squared is 36. And then we take the square root of it. So our standard deviation for this population is 1.63. And that makes sense, because if our mean is 6, remember 99.8% of our data will fall within 3 standard deviations either side of the mean. All right, so 3 times 1.63 is almost 5. And if we go 5 either side of 6, that captures the vast majority of the population. All right, let me turn that off. Let's go to side 2. So now we're going to take that population data, and we are going to create a sample distribution of sample means using those 3 numbers, 4, 6, and 8. So the first thing to do is we got to kind of randomly create every possible combination of 2 of those 3 numbers. And that's what we did in this table here. We got 4, 4, 4, 6, 4, 8, 6, 4, 6, 6, and 6, 8, and 8, 4, 8, 6, and 8, 8. And remember, we're doing sample distribution of sample means. So we're going to take then the means of those 9 combinations of numbers. And that's what I have in the red boxes here. Right? Let's add them together, divide by 2. All right. Now we're going to create an extension table, or frequency distribution table. This is sometimes referred to using our sample distribution of sample means. And then we're going to kind of compare and contrast it versus the population. All right. So we've got means of 4 through 8. Just took that right off the table above it. You got 9 possible theoretical outcomes. We had 1 4, so that's 1/9. We had 2 5, so that's 2 9ths. We had 6 3, so that's 3 9ths, and so on. We add them all the possible outcomes, and we get 1. So that's a check, and that's correct. And then in column 3, we multiply column 1 times column 2. Just like what the header says. Okay? So 4 times 1/9 is 4 9ths, 5 times 2 9ths, 10 9ths, and so on. We add them all together and we get 6. Well, the sum of column 6 is always the mean, right? And if you recall, the mean of our population on the front side was 6. That makes sense. The mean of our sample should be the exact same mean of our population, because, all right, if it's not, then we don't have a representative sample of the population. If we round numbers, if we had not used 9ths and we had actually used decimals, we probably wouldn't have gotten 6, but we would have gotten something super, super, super close to 6, within a couple hundredths of 6. All right. Column 4 we need so we can calculate the standard deviation of the sample. Also the standard error. So it's just column 1 squared times column 2. 4 squared is 16 times 1/9 is 69. 5 squared is 25 times 2 is 59, and so on. And we sum that up for 37.33. There's our mean of our sample. Here's our formula for calculating standard error / standard deviation of our sample. Here's column 4. Here's column 3 squared. We subtract, take the square root, we get 1.15, right? We're going to talk about this in just a minute. All right, so I think everybody's good there. Let me scroll up and let's look at some visual things. Again, as part of our inferential statistics. I'll leave both tables there so we can see them. Okay. So if we graph, the next thing is they want you to graph that table from above. So we've got means of 4, 5, 6, 7, and 8. We got probability over on the y-axis or vertical axis. And if you look, we went from that box or graph on the first page to a bell-shaped standard normal curve, which was the whole goal objective of taking a sample distribution of sample means. That's part of that central limit theorem and law of large numbers, which states as if I increase my sample size, I can get any set of data from a population that may not been normal to trend towards a standard normal distribution, which then gives me the opportunity to do all those probability calculations like we've been doing probably over the last 3 to 4 months. So, because that area under the curve directly corresponds and equates to probability, which we're going to find out here in future problem sets. All right, so let's look a little more deeper into the weeds. So does the mean of the population equal the mean of the sample? Yes, both turned out to be 6, and that always should be true unless we do some rounding. They should be exactly the same or very, 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 very close. All right. Does the standard error of the sample distribution, let's calculate it using this formula here that we're familiar with, which is a standard deviation of the population divided by our sample size at 2, and it came out to 1.15. Now, if you look back on our table immediately above it, where we calculated the standard error of the sample distribution using the data from our frequency distribution, we also came up with 1.15. Those two methodologies of calculating the standard deviation of our sample distribution should always equate to the same number. All right, so that's another good check. And anytime we do a sampling distribution of sample means, as I mentioned just a few minutes ago, if the population data was, if you already knew that it was approximately normal or standard normal curve, then the sample distribution is a given. It too is going to be a standard normal curve. But if you recall from those numerous series of 4 series of graphs with different sets of data where we kept increasing the N or sample size, every single one of them, if we got that in large enough, will naturally trend towards a standard normal curve, which then affords us the opportunity to calculate a multitude of probability situations. All right. Sound good? Okay. Let's stop sharing there, and let's go to, let's see, that was that one. All right, we're going to just briefly run through slide 1 because I think this is where I actually recalled to turn the video on. All right, so here we go. All right, so this is kind of a good summation of chapter 7, as well as a lot of what we learned clear back to late August of the last year, the beginning of this year's school year. Right. So what's the total measure there in the probability distribution? It's always equal to 1. Remember, this whole thing is based on area under the curve, right? And we fill from left to right, starting with 0, 0 clear over on the left side, getting all the way up to 0.999999999. We get clear over here on the right side. All right. Sum of all probabilities, sum of all outcomes always equals 1. If we multiply it times 100, it'd be 100%. It says, next one, justify the statement X bar becomes less variable as it increases. Yes, sir, because as we increase the N, the standard deviation, our standard error of the sample will get smaller and smaller. All right, let's put this to practice and prove it mathematically. All right, so I've got a standard deviation of 25 from the population, and I'm going to have a sample size of 16, 36, and 100. So using this formula in number 2, I'm going to calculate what the standard error of our sample distribution would be. So if it was 16, we'd have a standard deviation of 6.25 for the sample distribution, as opposed to the standard deviation of the population, which was 25. I'll increase that sample size to 36, it goes down to 4.167. And if I increase the N to 100, we go down to 2.50. And why is that? Because if I keep increasing the sample size, all right, my standard deviation, standard error keeps getting smaller and smaller. Standard deviation / standard error is a measure of variability or measure of dispersion of the data. All right. If that value gets smaller and smaller, this curve gets taller and taller. All right. Because the data begins to congregate about the mean. If you look at my, this 6.25 versus the 2.50, this curve would probably be, look something along this side, like this. Flatter, broader, more dispersed, more data on the left and right edges. But the area under both those curves, whether it's the green curve or the red curve, always equals 1, right? And that's why it's kind of like a balloon. If I push on the sides and make the center go up, I'm still going to cover that same exact area. All right. Questions on that? Let me scroll up and we'll do the bottom of this, and then I think we're back before we stopped. All right, let's do this. Clear. All right, so we are going to now look at questions 7, 8, and 9. So a certain population has a mean of 500 and a standard deviation of 30. Many samples of size 36 are randomly in the means calculated. Randomly selected. I think I'm missing a word there. It says, what value would you expect to find the mean of the sample? 500. The mean of the sample should always be the same as the mean of the population. Otherwise, you don't have good samples. And if you don't have good samples, how can you make conclusions as far as inferential statistics about the population? All right. It says, what value would you expect to find for the standard deviation of all the samples? Same formula as we utilized in questions 3, 4, 5, and 6. So it's standard deviation of the population divided by the square root of our sample size, which is 5. So we went from 30 down to 5, right? 30 down to 5 for a standard deviation means that data is congregating closer around the means, and the outer edges to the left and right are coming towards the center. And lastly, what shape would you expect the distribution of all these sample means to have? Anytime you do a sample distribution of sample means, the entire purpose is to get that thing to be a standard normal curve, so I can use all those tools to calculate probabilities of that specific data, just like we've done over the last dozen weeks or so. Questions on that? All right. Let's see, I'm trying to recall where we stopped the tape, or started the tape, I guess. We'll do this top half just to be safe. All right, let's talk about this very briefly and concisely. Okay, so here we go. It says a September 2006 USA Today article titled "Average Home Has More Televisions Than People" stated that Americans watch 4.58 hours of television per day. If the standard deviation for the number of hours television watched per day is 2.1 hours, in random sample of 250 Americans selected, the mean of this sample belongs to a sampling distribution. And anytime we do a sampling distribution, if I increase that n or sample size, it's always going to trend towards approximately normal. Standard normal curve, bell-shaped curve. And that is the law of large numbers and the central limit theorem. And our standard deviation is going to get smaller and smaller, and that data from the outer wing starts coalescing or congregating and moving towards that mean, right? Forming that nice bell-shaped curve. And we just demonstrated that, showing you 4 graphs of different sets of data from the same population, and we kept increasing the sample size, and we had box graphs or even stuff that looked like a V for the population that we kept increasing in the end, that eventually trended towards the standard normal curve, which then affords you the opportunity to calculate a multitude of probability calculations, limitless number. What is the mean of the sampling distribution? All right, the mean of the sampling distribution should be the exact same mean of the population, which is 4.58 hours. All right, the mean mean of the two should be exactly the same unless there was some rounding. In that case, it should be very, 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 very close. Otherwise, you don't have a good representative sample. What's the standard deviation of sample distribution? Same formula that we harped on side one. So it's the standard deviation of the population divided by our n, which it went from 2.1 to 0.133. So you can see that really shrunk, meaning that data really started congregating closer and towards the mean. That's a big shrinkage. Less variability, which gets into these 4 questions down below, all right? So the researcher wants to take simple random sample of about 5% of the student body of each of 2 schools. The university has 20,000 students, the college has 5,000. Identify each of the following as either true or false and justify your answer. It says the sampling variability is the same for both schools. That is false, because our N, or our sample size, if it's 5% of each schools, I'm going to have a much larger N for 5% of 20,000 than 5% of 5,000. All right, so my variability, meaning my standard error, standard deviation, is going to be much smaller for the university of 20,000 than it is for the college of 5,000. Number 14 says the sampling variability for the university is higher than that of the college. Exactly the opposite. It's the sampling variability for the university is going to be less because my N is going to be larger, right? As I increase the N, my variability is going to decrease, which when we talk variability, we're talking specifically standard deviation, standard error. 15 says the sampling variability of the university is lower than that for the college, right? So that's the exact opposite of question 14. So that is going to be true for the same reasons we said false for number 14. And number 16 says no conclusion about the sampling variability can be stated without knowing the results of the study. That is incorrect. It's just using the mere math, taking 5% of 20,000 and 5% of 5,000 with that formula with the square root of n in the denominator, we know the variability is going to be smaller with that larger n, which is the university, because of the larger population, 20,000 that we're drawing from versus the 5,000. Hope that makes sense. I'm going to stop the tape here, and then that should at least overlap with where I recall that I had not turned the tape on. Everybody have a good day, and we will see you later.